Okay, so we've done a couple examples, and now we've put into place all the analytical and mathematical tools that we're going to use for us to analyze AC power systems. In nearly all of the electrical grids, electric energy is supplied in the form of sinusoidal circuits. So primarily in these cases, we're interested in what we call average power. This is the power delivered or supplied to a pair of terminals over one full period of the sinusoidal quantity. We're going to see that power is not just measured in watts like it was in resistive circuits. There's new measurements for things such as reactive power, complex power, and apparent power. So now we're going to kind of investigate all of these quantities, if we can advance at all. So this graph that we're showing here, it's showing some instantaneous curves. First we've got voltage, second we've got current, and third we've got power. So let's just kind of look at those real fast. The voltage curve is labeled E in your diagrams that you've been provided. That's this curve right here. Okay, I'm going to draw current in green. Apparently I'm not drawing current in green. Okay, current in green, let's try it again. Sorry about that. Okay, and then let's draw power in blue. Good enough. And in this case, you'll notice that the voltage and the current are out of phase. We've picked an arbitrary angle here, theta, right? They're out of phase. That means you can see that this is where the voltage crosses the red graph voltage crosses the x-axis here. The green graph, the current, crosses the x-axis there. The difference in angular terms between the x-axis crossing is the phase shift. And here we've just labeled it an arbitrary theta. And in this case, we see that the voltage crosses first, and therefore the voltage leads the current. What we can say about this graph is that it's always true is that the formula P equals IV will hold true for instantaneous conditions. What I mean by that is it's always true that the instantaneous value of power is equal to the instantaneous product of current and voltage. If I wanted to write that as a math equation, I would write power of some time t1 is equal to voltage of that same time t1 times current of that same time t1, right? If I look at anywhere on this graph, I see that power at this point right here is equal to the product of voltage right here times current right here. It's a little hard to see there. It's really easy to see at the zero crossings. Anytime either voltage or current crosses the zero axis, well, power has to be zero. If there's no current, there's no power. If there's no voltage, there's no power. We see that there's a zero crossing here for current and for power. We see that there's for voltage and for power. And here we see that there's a zero crossing for current and for power. So we can say any instantaneous time t1, the power at that time is equal to the voltage at that time times the current at that time, where t is the same throughout, i.e. at any instant. The power equals the voltage times the current at that instant. So this graph is showing, again, instantaneous curves for voltage here in red, for current here in the greenish color, and for power in blue. And again, remember that they're out of phase by some angle theta, and in this case the voltage is leading the current. We could have also said there that the current lags the voltage, by the way. So again, we can see that the instantaneous power curve is derived from the product of the E and the I curves. And mathematically, the power curve is the result of the multiplication of two sinusoidal quantities. We say that this power curve, the blue curve, is at any time lowercase p of t is equal to lowercase v of t I of t, right? The time variant power in this circuit is equal to the time variant voltage times the time variant current. If I were going to write this in terms of the sine and the cosine functions, I would say the time variant power function, or the time domain power equation, is equal to Vm, or the peak value or the max value, V peak, cosine of omega t plus phi, times I peak, cosine of omega t plus phi. And that, since we have two phase shifts, we're going to have voltage and that. So P of t is just V peak, I peak, times the cosine of the voltage argument, cosine of the current argument. So since we're operating in the sinusoidal steady state, we can choose any reference we wish for the zero time. Like I said, it's very convenient to choose voltage as the reference. And what that's going to do is the theta v is going to go to 0. And this we're going to represent as just minus theta. So a lot of times we'll rewrite P of t is equal to V peak, I peak, cosine omega t, cosine omega t minus whatever that phase shift is right there, minus phi, or theta in this case. So the angle theta here is positive when current lags the voltage, and it's negative for leading current. And so you would say that, remember, theta is equal to theta v minus theta I. Using some trigonometric identities, we can rewrite this result. And we do this to get what we call the standard equation for instantaneous power. I'm going to not actually apply the trig identities. We could waste half an hour doing that. I'm just going to give you the result of applying these trigonometric identities of cosine of theta times cosine of theta minus phi. And what we'd see then is that we can write the instantaneous power, sorry, not the instantaneous, the time variant power as equal to V max I max over 2 cosine of theta plus V max I max over 2 cosine theta cosine 2 omega t. All right, and then we've got a third term, V max I max over 2 sine theta sine 2 omega t. So, huge equation, right? Wow. Don't worry about it, though. We won't actually often use, if ever really, this equation for doing calculations. The reason we write the standard form is because it's very useful to understand exactly what's going on in an AC power situation. Sorry, I'm having some troubles with my remote. It's not liking to advance the slides anymore at all. Oh, there it went. So let's make some following observations relating this equation to the graph. From this graph, we can see that both the voltage and the current do one complete oscillation, but the power does two complete oscillations. We see that the power waveform makes two complete cycles in the same time it takes the current and the voltage to make one complete cycle. Another way to say that, saying the same thing, is the frequency of the instantaneous power waveform is twice that of the voltage of the current. We can also see that in this equation because they have these cosine and sine terms, 2 omega times t, right? We know that the frequency of the voltage and the current is just omega t, cosine of omega t. Well, in the power, it turned up as cosine of 2 omega t, twice the frequency. We're also going to note that the instantaneous power can be negative for a portion of the cycle. We see that right here in this area, for example, we've got negative power. This is true even if the network that's consuming power is entirely passive. You know, resistors, inductors, and capacitors. We can still have negative power. So how did we get negative power? In a completely passive network consisting of only resistors, capacitors, and inductors, this negative power implies that energy that had been stored in the magnetic and electric fields of the inductors and the capacitors, or the inductance and capacitance of the system, is now being extracted. So it's actually flowing out of those magnetic fields during that case, right? Magnetic and electric fields. So you'll notice that if theta v equal theta I, sine of theta is 0, or sine of 0 is 0, excuse me, and so this third term would drop out, and so any sort of component related to that would be dropped. That also proves that power can't be negative in a resistive circuit, which makes sense since a resistor can't store, any sort of energy in it.